Welcome to this channel Chemistry Made Easy by Dr.ARM. Today we will discuss the next part of the topic, that is molecular orbital theory is our running part of this topic. And last time we have seen the formation of molecular orbitals using s orbitals only. Now we are going to see the formation of molecular orbitals using p orbitals. So this is our title, that is how are molecular orbitals formed from p orbitals. So in this discussion we are also going to see why we choose z axis as an internuclear axis. Similarly, we also understand why are the atomic or molecular orbitals called sigma or pi atomic or molecular orbitals. It means what is indicated by this sigma and pi. How is molecular orbital diagram drawn for a given linear combination of atomic orbitals? And last, how does the signs of wave function matter in linear combination of atomic orbitals? So we will begin with this first point, that is linear combination of atomic orbitals resulting in the formation of molecular orbitals. So we have seen in previous topics how are these s orbitals and p orbitals have the shapes of their electron clouds. So we have seen that the spherical shape is shown by the s orbitals, whereas this type of shape is shown by the p orbitals, or this type of shape is also shown in this way. So we can draw these lobes like this. So the lobes are also shown in this way. So this is the z axis. So this is also the z axis, and the lobes are shown in this way. So here this is pz orbital. So this pz orbital has the signs of wave functions such as say minus and plus. So one lobe has the minus sign of wave function and another lobe has positive sign of wave function. And other axes are also lying in this way. So other axes are lying perpendicular to this. So we will show these in diagram. So linear combination takes place. So if we take the example of say it is 1px A, so it is px A plus px B, and this will undergo linear combination of atomic orbitals to produce the molecular orbitals called sigma plus sigma star. That is, one is bonding and another is anti-bonding. Anti-bonding. Now we will see how are these atomic orbitals and molecular orbitals shown in order to understand the pictorial representation of this linear combination of atomic orbitals. So here we will see first the px orbital. So we will show this as say this is z axis, this is x axis, and this is y axis. So this px orbital means in order to form linear combination or undergo the process of linear combination of atomic orbitals, we should have at least two atomic orbitals of the same or different nature but of the different atoms. And now we are going to see how this z orbital So we will see first pz orbital, not x orbital, but pz orbital. This pz orbital. So we have shown that these orbitals are lying in the direction of z-axis, and we can show these orbitals in this way. So these orbitals are shown in this way. Now here, the signs of wave functions, say this is minus and this is plus. So the signs of wave functions are opposite to each other. Similarly, we will show another type of orbital. So this is also z-axis, this is y-axis, and this is x-axis. This is y and this is z-axis, and we will show again the atomic orbitals. These are the lobes of pz orbital. And they have the same type of signs of wave functions, say minus and plus. Now, first of all, we will see why we have chosen this z-axis as the internuclear bonding axis or internuclear axis for linear combination. This is because the s atomic orbitals that undergo the linear combination is considered or studied easily because there is no much more complication. But as we go from or switch over to p orbitals and d orbitals, the complex process begins. The linear combination of atomic orbital becomes more and more complex. So in order to make it convenient or easy to draw or consider, we are considering this internuclear axis as z-axis, so that it will be easy to explain the linear combination of atomic orbitals in further d orbitals, etc. in multi-atom systems. So we know that this is, say, p z a and this is p z b. So after linear combination, LCAO, after linear combination, we will get that is addition type of overlaps. So this will give us addition type of linear combination, and this will give us subtraction. Type of linear combination. As a result of this, the process will give us like this. So this is our z-axis, this is y-axis, and these are the x-axis. Here we know that these lobes are moving, or when the signs of wave functions are same in pointing in one direction, means plus sign of wave function and this plus one sign of wave function is pointing in this direction, and the negative sign of wave function is pointing in opposite direction. Then in this case, the two atomic orbitals will undergo subtraction type of overlap. between these two atomic orbitals, and this will produce the molecular orbitals containing the structure like this. So this has plus sign of loop function. This will have the minus signs of loop functions. So this will have also minus sign of wave function. So when the signs of wave function, so this is obtained because of subtraction type of addition, that is linear combination, and this will give us the nature of molecular orbital called as sigma. So this will generate sigma pz molecular orbital, and in this case the electron density from both the atomic orbitals, that is every lobe, is moving at the center of the two nuclei, and therefore the electron density increases, and it results in strengthening of the bond. Again, if we consider the addition type of overlap here, then we will get this type of arrangement. Like this. Here, because of the addition type of overlap, the signs of wave functions becomes opposite to each other. The signs of wave functions are becoming opposite to each other. So as a result of this, the lobes are shown in this way. Like this. So here you will find that the signs of wave functions are, say, plus and minus. So here it will be plus and here it will be minus. So we will get this another molecular orbital which is named as sigma star pz. Sigma star pz. So this is our antibody molecular orbital, and this is our bonding molecular orbital, and this is antibody molecular orbital. So because of this antibonding nature means the signs of wave functions are opposite. Their repulsive forces are developed between these two clouds. As a result of this, their energy increases, and in this case you will find that the two lobes are added together like two mathematical terms. As a result of this, two electron clouds come together and it becomes a larger electron cloud, as a result of which the electron density is concentrated between the two nuclei. So this strengthens the bonding effect, and whereas this, because of repulsive forces, this weakens the bonding effect, or whatever the bonding effect is created by these electrons or electron cloud here is cancelled by these repulsive forces existing between these antibody molecular orbitals. So in this way we can understand how the bonding molecular orbitals are formed. Then we will come to know how are these non-bonding or pi electron clouds are formed for the formation of pi MOs, molecular orbitals. For this purpose, we will see the two examples. That is, say example, this is z-axis, and we know that there is, say this is x-axis and this is y-axis, and we are taking, say, the example of px. Say this is pxa. So here the pxa will have the electron cloud like this. So the electron cloud is oriented in this way. Like this. And the signs of wave functions are like this. Say this is plus, this is minus. Again, we will see. So this is one electron cloud for the atomic orbitals. So we have seen that this is z-axis, this is x-axis. Now we say plus. So these are the same axis, and z. And we will have also same type of orbitals, pxb, another atomic orbital. So there is electron density concentrated in this way. And the signs of wave functions are also in the same way, plus and minus. These are the signs of wave functions. So, being these parallel to each other, they can show that they can be viewed as a single orbital. So, when we view this is the internuclear axis, say in this direction, and z-axis is perpendicular to it, going this way. So, the two lobes appear like this as a single lobe, but there is another hidden lobe, so that is not appearing. So there is another lobe like this. So sometimes it is represented in this way. So this is px orbital. And when these two orbitals undergo linear combination with each other, LCAO, they will undergo this type of, that is addition type of overlap, means the plus plus and minus minus signs, plus minus signs of additions will take place. Here, as a result of this, we will find that this is x-axis, this is also x-axis, and we are having the molecular orbitals of this type. So the two atomic orbitals or molecular orbitals will overlap with in this way. So you can observe this is the outer atomic orbital. This is also outer atomic orbital, and the two atomic orbitals means so we will correct this. Like this. So the two atomic orbitals are converted into two electron clouds like this. this is one electron cloud and this is another electron cloud, which is lying in the ZX plane. This is ZX plane. So we'll have the signs of wave function. Say minus is on one side, plus is on one side. So this will give us the pi px bonding molecular orbital. Similarly, we will get, because of the opposite signs of wave functions, we will get the atomic orbitals, which are oriented in this way. So in this way, the anti-bonding effect will be observed here. Say this has minus sign of wave function. This is minus, this is plus sign of wave function. So in this way, you will have this type of bonding, that is the central region, means the region between the two nuclei is empty, there is no electron cloud. And the result of this is called pi star antibonding molecular orbital, that is pi star molecular orbital. So here sigma indicates that if electron cloud is present, say this is the electron cloud, and after rotation about this axis there is no change in sign, of wave function, So sigma indicates that it may be atomic orbital or molecular orbital. But if it is rotated about the internuclear bonding axis, then it does not show change in sign of wave function. But on the other hand, when the orbital is like this, you can consider this atomic orbital, molecular orbital, or these atomic orbitals. So if we rotate these atomic orbital about this z-axis, then you will find that it will show change in sign of wave function. Means minus sign will come here, plus sign will go there. In this way, these orbitals are having pi orientation. So they are having pi orientation. Similarly, you will find that if you rotate these orbitals against around this bonding axis, you will find that the plus signs will go there and minus signs will come here. So there is change in sign of wave function. So this change in sign of wave function is indicated by pi. So pi orbital, pi indicates the change in signs of wave functions of these orbitals. It may be atomic or molecular orbital after rotating it around the internuclear axis. So this is the indication of sigma and p orbitals. So similarly, you can also take this, instead of px, you can consider this py orbital. So we can also have such type of effect. So if we consider this as y-axis, z-axis and x-axis, and according to this the lobes are lying in this way. are lying in the direction of y-axis. So we can show the signs of wave functions with like this. Similarly, we have also the lobes in this way, and the lobes of these atomic orbitals are lying in this way. So it will show the signs of wave functions like this, plus and minus. So after linear combination LCAO, we get that addition type of overlap and subtraction type of overlap. So this will produce the bonding molecular orbitals and anti-bonding molecular orbitals like this. And as a result of subtraction means addition type of overlap here it is in case of these py orbitals, there is here addition type of overlap, addition, and here it is subtraction type of overlap. As a result of this, you will find that the lobes of these are formed in this way. The two lobes will come together like this. So you will have the empty region between these. Like this. And they will have the signs of wave functions like this. So plus plus will come together, minus minus will come together. So this is plus plus and this is minus minus. So this will produce the pi p y orbitals. These bonding molecular orbitals. Similarly, we will have the molecular orbitals of antibonding nature. So here you will have the molecular orbitals like this. So these are having the orbitals like this. So like this, and the signs of your functions are plus, minus, minus and plus. So this is pi star p y orbital, that is antibonding molecular orbital. So in this bonding molecular orbital, the electron density is concentrated between the two nuclei, but one is above the plane, above the internuclear XY plane, and below the ZX plane. So here this is bonding MO and this is anti-bonding MO, anti-bonding MO molecular orbital. So every addition of electron into such bonding molecular orbital will increase the strength of the bond, and every electron that goes into this antibonding molecular orbital will decrease the strength of the bond. So in this way, the bonding effect is created by this molecular orbital if it contains any electron. When antibonding molecular orbital creates antibonding effect, that is, the bonding effect is cancelled by the electron present in it. Then we will show the MO diagram for these molecular orbitals which we have seen here. So this is the energy axis, and we can have these three atomic orbitals, that is p, and these are also p atomic orbitals. So there is px, pz, px, py. Here is also pz, px, py. Then the linear combination that results between the pz orbitals gives us the sigma pz bonding molecular orbital. Similarly, the antibonding molecular orbital will be formed by linear combination of the linear combination between the px so there are two such orbitals, that is pi x and pi y molecular orbitals. Similarly, we have these two pi molecular orbitals, pi star x and pi star y. And finally, we have these. This is sigma star pz orbital. Sigma star pz orbital. So energy axis is like this. Two atomic orbitals means p orbitals are lying at the same energy level, but during linear combination, the bonding molecular orbital shows loading in energy. Antibonding molecular orbitals are showing increasing their energy. So every electron that enters into this bonding molecular orbital creates bonding effect, and it will strengthen the bond. And every electron that enters into these antibonding molecular orbitals will weaken the bond produced. So this is about these orbitals. Now we should also know that these non-bonding molecular orbitals, non-bonding amines. For example, if we have say this s orbital plus, if we are having then orbital like this, say that is pz orbital. It is pz orbital. Then the linear combination takes place. Linear combination takes place, and it gives bonding and antibonding molecular orbital. But if the two orbital